All right, number 10. Which of the following statements are true? Okay, so we got to look at each of these one at a time. The first one says if f has a local minimum at a, then f prime of a equals 0. That is not always true. I mean, at first, you think, oh yeah, if our curve goes like this, right there, the slope is 0 because we have a horizontal tangent line. So that means f prime of a equals 0. But what if we had this? This would be a minimum. And for this problem, since that's a cusp, f prime is undefined. Does not exist. Well, right there. And let's say that's at A. So this problem is out. It's only half true. The next one says f prime of A equals 0 and f double prime of A equals 3. Okay, so those are two facts. Then f has a local minimum at x equals A. So what does that tell us? Well, this tells us, but this one tells us that we definitely have a slope of 0 at A. So if this is A right here, we have a slope of 0 right there at A. And then because f double prime is a positive number, we know that the curve is concaving up. Therefore, we definitely know that there is a minimum at x equals A. So number 2 is true. Let's read the next one. If f prime of A equals 0 and f double prime of A equals 0, then f does not have a local minimum at x equals A. So at first, when you think about this one, since we also have a slope of 0 here, we're thinking maybe it looks like this. But then you might have saw this, and you go, oh, hey, if f double prime equals 0 at A, that means there's an inflection point right there at A. And so you're thinking like this. First we're concaving up, and then we're concaving down. We have a horizontal tangent line right there, but the concavity changes, therefore there's no minimum there. However, just because this equals 0 does not mean that there is an inflection point there. We can still have something like this with an inflection point for some reason equaling 0 right there. So this last one is not entirely true. It is almost true. This does not mean that there's definitely an inflection point there. The only way we know there is an inflection point is if we did something like a sine line graph with the f double prime, and at A, the concavity changes from plus to minus or minus to plus. But if it goes plus to plus, and A still makes f double prime equals 0, then this is not an inflection point anymore because the sign did not change. All right, so that means our answer right here is B. All right, trig. Okay, so we're given f prime, and these are the only x values that we're looking at, x values that are between negative pi and positive pi, and we're looking for critical points. So what we got to do is we got to take this x times cosine squared x and set that equal to 0. Now we have two factors here multiplying to each other to get 0. One is definitely going to be 0 because of that factor right there. The other one we got to do a little bit more thinking about. Okay, so we got x squared of x, or cosine squared of x equals 0. Now let's just ignore the squared for a second. Where on our unit circle is cosine equal to 0? Now we can rephrase our question. Instead of saying where is cosine equal to 0, we can say where does x equal 0 on our unit circle? And you should say right here and right here. So this dot right there would be pi over 2. And then this dot right here, that would be 3 pi over 2. So at first, it looks like our answer is going to be pi over 2 and 3 pi over 2. But there's a problem. Well, first let me confirm this with you. If we plug pi over 2 into this, cosine of pi over 2 would be 0, and then when we square it, we still get 0. So the square doesn't really matter right there. It's just kind of a distraction. And the same is true for 3 pi over 2. Now, the problem that we're having is that, one, we don't see 3 pi over 2 right here. But they could put 3 pi over 2 right there and you'd be wrong, because 3 pi over 2 is not in this interval. 3 pi over 2 is kind of like saying 1 1/2 of pi, which this is going to be more than pi, so it's not in that interval. So what's another way we can represent this dot? Another way is to go the opposite way. So that would be negative pi over 2. So instead of writing 3 pi over 2, we're going to write negative pi over 2. And that would be it. We don't have to go around the unit circle more, because these there's not going to be any other angles that are in our interval. So we have a critical point at 0, at pi over 2, and negative pi over 2, which means our answer is C. Let f equal that, and it says the graph of f has which of the following lines as horizontal asymptotes? Ooh, that's a problem, because normally when we get these problems and we're looking for horizontal asymptotes, we can just use algebra. And we look at the degree of the numerator and the degree of the denominator and make our decision based on that. But we have a square root on the denominator that kind of messes things up. So we have to go to our calculus way of finding a horizontal asymptote. And that's by taking the limit as x approaches infinity of the function. All right, so let's try it. If we plug in infinity in the x on the numerator and the x on the denominator, what's going to happen? Now, earlier in chapter 2, we learned other ways to solve this, but now we have L'Hopital's rule. But we can only use L'Hopital's rule if we get an indeterminate form. So let's plug in infinity in the top. If I plug infinity into this x, this number on the numerator is going to go towards infinity. Just think about the graph of 3x. If you think about the graph of 3x, it goes like this. And as we go to infinity, this also approaches infinity. So we get infinity on the numerator. And then we have the denominator. Here's a little different. It's kind of weird. We're going to square the infinity, which just makes the infinity even bigger. And when we take away 1, that doesn't even really matter because we're approaching infinity. And then we have the square root function. The square root function is just going to make the number smaller, but we're still going to be approaching infinity. Just think about the square root function. It goes like this. The square root function right here also is going towards infinity as we go towards infinity on the x-axis. So it looks like we do have an indeterminate form. We have infinity over infinity. Yay! Now we get to use L'Hopital's rule. So to do L'Hopital's rule, we just take the derivative of the top, and we take the derivative of the bottom, and then we take the limit of that as x approaches infinity. Let's see what happens. On the top, I get 3, and on the bottom, let's see, we got x squared minus 1, and that's raised to the 1/2 power. If I take the derivative of that, it's going to be 1/2 times x squared minus 1. Raised to the negative 1/2, and then we are going to multiply it times 2x. The 2 and the 1/2 cancel out, so we just have an x multiplying to it. And then we get x over x squared minus 1 raised to the positive 1/2 because it was negative, so I'm just going to put it on the bottom with the x. So now we have x, and we have x squared minus 1. We can rewrite this since we have a fraction inside of the fraction. We can multiply the top and bottom by this denominator, and we would get 3 times x squared minus 1 raised to the 1/2 power divided by x. So let's take the limit of this as x approaches infinity to see if we get anything different. The denominator clearly approaches infinity. The numerator, we saw this guy before. He's just going to go approaching infinity again. He is the same as this guy right here. So we got infinity over infinity again. So let's take the derivative of the top and the bottom one more time to see if we get a different result. The bottom we just get 1. So we're going to take the limit as x approaches infinity. On the bottom we get 1. On the top, let's see. We drop the 1/2. We would get 3 over 2. and then we would get x squared minus 1 raised to the negative 1/2 power, and then multiplied by 2x. The 2 and that 2 will cancel out. It looks like we almost have the same situation happening. This guy is going to go on the bottom. We have 3x staying on the top, and then we have x squared minus 1. It's like we're going in circles. Now don't get frustrated if it doesn't work, if L'Hopital's rule doesn't work. We're just going to have to do this the old-fashioned way. So I'm going to write 3x over the same thing as before, except this time I'm going to take an x squared out of what's inside the square root. Now that will allow us to take this x squared out of this square root and give it its own square root so that it looks like this. And so once we do that, we can simplify that square root of x squared, and then we would get 3x over x times the square root of x, 1 minus 1 over x squared. So let's take those x's and cancel those out, and then take the limit of what we have left over as x approaches infinity. Now we're going to plug infinity into this x, and when we do that, the bottom of that fraction gets infinitely big, and whenever the number on the denominator gets way bigger than the number on the numerator, that number goes to 0. So that means we just have 3 over the square root of 1. So that means our answer is going to be 3 divided by 1 or 3 divided by negative 1, because the square root of 1 is plus or minus 1. That means our answer is B.